Hello group, we're going to start chapter 6 now. This first section is just using formulas to solve problems. The next section we'll be looking at rearranging formulas. So for the most part we've looked at measurement formulas with volume and surface area. You'll see some of those in this section, but most of the formulas that you'll see that you may not recognize will be provided for you. First, we're just defining what a formula is. It's an equation, but the difference between an equation and a formula is that a formula is going to relate two or more variables, but they represent real world quantities. So a formula is usually an equation that gives you something practical, okay? We're going to go through some examples here. You have a worksheet that in class you'll fill in the definition for the formula. You'll also use two formulas for height relating to the radius and the femur bone in male and female, and you'll have a chance to test how accurate those formulas are. We have a summary at the bottom of that, which helps you to plan and organize your solution when you're working with a formula. Questions you can ask that help you, strategies that you can use. And then the assigned work for this section, we'll have you look at some parts from a few questions on page 346. You get to choose from a pair or sets of questions, and then a feedback question from 10 or 13. So I'm just going to go through the examples which are in your textbook as well on pages 343 to 345. I'll just work through the solutions and you can compare to what you see in the textbook. Let's get started. This first example is using something called Young's formula. This is a formula that a nurse would use to decide what the dose should be for a child of a given age, G years, comparing the child dose to the known adult dose, which is A in milligrams, and the child's dose is C in milligrams. So if we were to, for example, use a 3-year-old child, then our G value is 3 years. Our adult dose is given at 600 milligrams for that particular medicine. Okay, the formula here is fairly simple to work with. It's a fraction. AG could also be interpreted as A multiplied by G divided by G plus 12. Here we're not questioning where this formula comes from, we're just using it, okay? So substituting in our values here, following order of operations, 600 multiplied by 3 divided by 3 plus 12. And we know our answer's supposed to be in milligrams. So in this case, if we were to put units in, we may find that putting in 3 years, and this is probably 12 years, that our answer in milligrams would probably be, because we're going to end up getting 1800 as a number, and that would have units of sort of milligrams, years, milligrams times years, and then the denominator we're going to have 15 years. So our answer there should have no years in the value, and it's easy to work out the math of that one. 1800 divided by 15 is 120. Okay, so the child dose should be 120 milligrams. So it's a really easy example of a formula to use. Order of operations, first we're going to multiply in the numerator or add in the denominator, and then finally do division. Let's move on to example 2. So this one is a formula that allows us to calculate the area of any triangle with side lengths A, B, and C. Here, the value of S is this average. All right, it's almost like an average. It's the sum of all 3 sides divided by 2. We're not really told what S is in the formula, but we are told that we can use S to calculate the area of a triangle. So here you might wonder, well, why would I want to use this formula? If you were to draw a triangle and you knew the side lengths, you know, let's just put some numbers in here just to work with. Let's say we had 12, 14, and say 5. Well, area of the base times the height is the area of the triangle, but here we don't have the height, and to get the height we would need to solve for this length here, which may be difficult to get. Okay, we might have to do a little bit of trigonometry there to solve for the length from this vertice all the way over to here, and rather than doing that, any triangle, according to this Heron's formula, can have an area calculated just based on this relationship. So again, we're not questioning where the formula comes from or how we would derive it, just using it. So in this margin, we see that there's a little bit of a tip, which is to plan our solution by working backward from what you are trying to find to what you are given. Write the solution by working backward. That's sometimes useful. In this case, we're trying to find the cost of fertilizing the lawn. So to get the area of this lawn, we've got the formula. To get the cost of fertilizing the lawn, I think we would need to know the area of the lawn multiplied by a ratio of 1 bag for every 900 square meters. And that would tell us how many bags we're going to need, and then multiply by the cost of 1 bag, which is $19.98 for every 1 bag. So we've got sort of some equivalences here which we can use to come up with this overall cost. So working backwards, that's the final step, and then before we do that, we need to know the area of the lawn. Now before we do that, we would have to know the area of the lawn, and we have the formula for that. Before we do that, we would have to know the value of that variable s. Okay, so those are our 3 steps. Now when we actually execute these, the first thing we need to know is the side length. So we have 150, 200, and 300. So we can just use them as A, B, and C. So our solution is going to be step 1, step 2, and step 3. So step 1 is S equals, get the formula A, B, and C divided by 2. So that's 150 200 and 300 divided by 2. So that's 650 divided by 2, it's 325. Okay, we can assume that that would be in meters, since we're just adding meters, and dividing by 2 gives us an answer in meters. Now we're going to take that, substitute it into the formula, all right, which is provided. I'm listing my values for A, B, and C on the side. I should have done that before. Strategies in the textbook include the following: making a checklist of variables and their values. So that really should have been included up above when I first calculated S. Now that I've got the value of S, I had A, B, and C before, so we're going to load these numbers into the formula and we'll calculate. Now here, the overall operation is a square root. Within the root we have multiplication, and within the multiplication we have subtraction, which is a priority here before multiplication, actually, because brackets are involved. So lots of operations involved in this. Just pause the video at this point. I'll work out the solution. You can compare your answer. Okay, this is a good example where showing steps is a really good idea. So I worked out the differences in the brackets, then I did the product of those. I got 177,734,375. Square root of that is 13,332, and I just rounded to the nearest square meter. Now in case you're wondering how all this gives square meters, well, this is meters and this is meters and all this is meters. So what we would end up with from this product here, which is this number here, this answer would be in meters to the 4th. Okay, and then we take the square root of meters to the 4th, we get meters squared. And you can kind of imagine going backwards, you're squaring, right? So anyway, that's how the units work out. Just make sure you have the correct value. I checked my answer twice to make sure that it was correct. Okay, not an easy formula to work with and a new formula, but again, just making sure we have our order of operations and we should be okay. The last example is something a little more familiar here. No formula is provided, but it's a familiar shape or pair of shapes. These aren't composite solids, so we just use our individual formulas for these. We have a bucket with radius 18 centimeters, a height 18 centimeters. We're pouring soil into a rectangular planter that measures 1 meter by 40 centimeters by 20 centimeters, and we're trying to determine how many buckets of soil are needed to fill that planter. Okay, so in this problem here, we could use our strategies. No formulas or relationships are given, so we'll have to determine that. The numerical information that's given should allow us to calculate all the volumes that we need. We won't need any additional information. However, we'll need to take notice of our units. We have some in centimeters and some in meters. So let's decide we're going to convert into centimeters. So conversion would be required there. Working out our solution, we could probably think of this one again as working backwards. First, we need to know the volume of the planter. Okay, so working backward here, we could probably look at the last step would be volume of planter divided by volume of bucket. And that will give us the number of buckets needed. Okay, so before that, we would obviously need those individual volumes. So volume of the bucket, that could be calculated right as is. The volume of the planter, that one can be calculated prior to that, but before we do that, we're going to need to convert all units to centimeters. All right, and then the formulas involved here for the volume of the bucket would be volume equals pi r squared h. That's a relationship we've seen before. The planter is volume equals length times width times height. And again, we've seen that one before. So these are simple relationships that we can just look up in our study guide or our formula sheet. Now we can execute the solution here and work out the final answer. So I'm going to have to convert units here. First step would be to convert my length into centimeters. So that's an easy conversion here. There is 100 centimeters in 1 meter. Now we can work with the strategy here, which is calculate the volume of the bucket. So this is our radius and this is our height. So we label those. We can label this length and this the width 40, and then this can be height. I'll use, in this case, I'll use capital H for height. So we have three symbols that are all unique. And now we can calculate the volume of the bucket. So pi r squared h with the radius and a height of 18 is the first step. So volume of the bucket is pi r squared h. I'll work it out at this point. You can compare your answer and we'll get the final calculated result for both the bucket and the planter. I'll do it all at once. Okay, pi r squared h, I get 18,322 cubic centimeters. Notice I'm putting my units in with my numbers as well, just to reinforce the idea that this is a three-dimensional quantity. So the exponent on the variable should be, or on the unit should be 3. Length, width, height. Again, I'm listing my values off to the side here. Substituting them into the formula, which I'm knowing in advance, and I'm calculating an 80,000 cubic centimeter volume for the planter. The ratio of the planter volume to the bucket volume would be the number of buckets required. I get 4.4 approximately, and so my conclusion can be therefore about 5 buckets are needed to fill the planter. Just review the steps for solving a problem like this, and the next section we're moving into right after this will be rearranging formulas. So you'll notice that with these problems that we looked at, we only solved for the formula as it was given. We didn't rearrange for one of the variables within the formula. So that would be the difference between the first and second section of chapter 6. Copy the definition down for formula as well into your worksheet when you come into class tomorrow. We'll go through this, investigate, and then you'll have a chance to work on the problems at the bottom of that. Okay, see you.